Mars today is cold, dry, and covered in dust and rock, but its surface still preserves chemical traces from a very different past. As rovers continue analyzing samples, some of those rocks are turning out to be more altered than expected. In several locations, instruments have identified kaolinite, which is a clay mineral that forms when liquid water interacts with rock for long periods of time.
At first, the readings didn't seem especially dramatic. Kaolinite isn't some exotic mineral. It doesn't come from a quick flood or a brief melt. The original minerals have to stay wet while their structure gradually breaks down and rearranges, likely over thousands or even millions of years. That detail makes it very different from most of the water evidence we already have on Mars. River channels and outflow valleys can be carved quickly by sudden events, but kaolinite doesn't form in those conditions. It requires stability. When this clay shows up inside ancient layers, it suggests an environment where water lingered, and where the surface stayed damp long enough for chemistry to slowly reshape the material itself. So the discovery hints at locations where Mars may have supported standing water, or groundwater systems, that persisted way longer than short-lived floods, shifting the picture from brief wet episodes to stretches of time where parts of the planet remained consistently altered by liquid water.
This isn't just a theory based on a single sample.
The recent data from Perseverance's SuperCam has identified over 4,000 of these individual white fragments scattered across the Jezero floor. They range from tiny pebbles to large, bleached boulders that stand out against the iron-rich red dust like bone. But there is a problem. When the science team looked at the bedrock, the actual ground the rover is sitting on, it didn't match. The white rocks are what geologists call float rocks. They aren't from here. They were transported, potentially washed down from the crater rim by ancient river systems. This tells us that the tropical Mars we're seeing wasn't just a small, isolated puddle in a crater. The source, the mother lode of this kaolinite, is likely miles away, sitting high on the crater rim or even further out on the Martian plains. We are looking at the debris of a massive regional climate system. On Earth, for a rock to be stripped of its iron and magnesium until only this white aluminum clay remains, it requires a specific chemical process. When analyzed through the SuperCam spectrometer, these rocks reveal a specific chemical state known as intense aqueous alteration. For kaolinite to form, the primary silicate minerals must be subjected to a process of selective leaching. This only occurs when a planet maintains a high-pressure, high-temperature atmosphere capable of sustaining a continuous liquid-phase hydrological cycle. We're seeing evidence of a sustained atmospheric greenhouse that lasted for millions of years. This discovery forces a massive recalibration of our models regarding the Martian volatiles, the gases that make up an atmosphere. While the solar wind did strip away much of the planet's shield, the presence of these hydrated clays suggests a more internal mechanical failure. It's possible that Mars didn't just lose its atmosphere to the vacuum of space, it may have chemically collapsed, with the planet's own crust acting as a carbon and water sink that permanently pulled the life-sustaining gases out of the sky and into the ground. The next phase of this investigation moves away from the surface debris and into the subsurface data provided by the RIMFAX ground-penetrating radar. While the SuperCam identified the kaolinite in these float rocks, the radar is now picking up massive, reflective layers buried hundreds of meters beneath the crater floor. These aren't scattered pebbles. They are continuous, high-density structures that suggest the white clay formations we see on the surface are just the top layer of a much deeper geological sequence. It raises the question of whether this tropical era was a surface-level event or if the entire crust was saturated and chemically altered from below. Adding to this is a specific isotopic signature found within the oxygen atoms of the clay. Initial readings show a higher concentration of heavy isotopes than expected, a sign that the water which formed these rocks underwent an intense period of recycling. On a planet like Earth, this happens when water is filtered through massive underground reservoirs before returning to the surface as springs. If this same mechanical process was happening on Mars, it may lead to a deep crust plumbing system that could have remained active long after the surface atmosphere began to thin. Solar models for the early system indicate the Sun was 30% fainter than today. Under those conditions, Mars should have been a permanent ice ball.
The physical presence of kaolinite suggests an internal heat source was overriding the lack of solar energy. Residual volcanic heat trapped beneath the crust functioned as a thermal engine. This internal mechanism maintained tropical temperatures even while the planet remained within a deep freeze zone.
The brightness of these white clay formations creates a secondary conflict. As this material expanded across the landscape, it reflected more sunlight into space, an effect that usually triggers immediate planetary cooling. High concentrations of sulfur dioxide functioned as a secondary greenhouse layer thick enough to override this cooling effect. Perseverance is currently sampling the surrounding sediment for these sulfur signatures to determine the exact point where this chemical balance failed and the planetary system began to lock up.
This chemical struggle eventually hit a threshold known as the sequestration limit. As the kaolinite formed, it began to physically absorb the atmosphere's primary greenhouse gases. The minerals acted as a massive filter. It was a runaway effect. The more the internal engine tried to keep the planet warm, the more trap minerals were produced.
What we are seeing in these white rocks is the forensic evidence of a planetary system that eventually turned on itself. Mars consumed its own atmosphere through a slow, irreversible chemical collapse. These thousands of white fragments scattered across Jezero are the physical remains of a tropical world that was literally pulled underground. As we move deeper into the 2026 mission data, it's becoming clear that the desert we see today is the final, frozen state of a massive mechanical failure that we are only just beginning to understand.
If you enjoyed this explanation, be sure to subscribe to be caught up on discoveries or mysteries happening in our solar system.